Rockets and mass drivers each promise to launch humanity into space, but which approach will take us further, faster, smarter, and cheaper? Today we'll be comparing not just two types of launch systems, but two fundamental approaches to space travel, rocketry and mass drivers. We'll explore the pros and cons of each approach, as both have distinct advantages and disadvantages. Most folks are already familiar with rockets, but mass driver is a less commonly known term. So first, let's briefly introduce mass drivers. Mass drivers can be a fairly broad category, including chemical-powered guns and railguns, but for our purpose today, we'll be focused on the category known as a linear motor. This is an electromagnetic propulsion system designed to accelerate objects, or payloads, to high velocities along a long track. It works by using electricity to generate electromagnetic forces to propel payloads, launching them into orbit or onto different trajectories. As such, payloads accelerated with mass drivers don't consume onboard propellant, avoiding the complexities of the rocket equation. This payload could be a cargo pod, though we often imagine as a spacecraft, which is equipped with thrusters and a small onboard fuel supply to help it reach orbital speed and maneuver in space, much like the Space Shuttle had orbital maneuvering engines for this purpose, and to later re-enter the atmosphere to land. To be useful for space launch, a mass driver needs to have four key characteristics. First, it needs to have low mechanical friction. Ideally, its payload glides along a track without direct physical contact. This enables rapid reuse rates without wear and downtime for refurbishment. Second, it needs to have low atmospheric friction. Ideally, a mass driver will operate in a near-vacuum environment, as high speeds will generate significant drag and heating in the presence of dense air. This makes them ideal for airless worlds like the Moon, but on Earth or Mars, where there is an atmosphere, the mass driver either must be situated at a very high altitude, such as on top of Mars' tallest mountain, Olympus Mons, or if that's not possible, then the launch track needs to be enclosed with an evacuated tube until it reaches an altitude where the atmosphere is thin enough for the spacecraft to travel the rest of the way up through it and out into space. The third characteristic of a mass driver relates to acceleration and track length. Exit speed is equal to the square root of twice the product of the acceleration rate and track length. So your exit speed depends on both the acceleration rate and the track length. Because of that square root, to double your speed, you need to either quadruple your acceleration, quadruple your track length, or you could double your speed by doubling both your acceleration and your track length. Same, you could triple both for triple the speed, or increase your acceleration or track length by a factor of 3 squared, or 9. So mass drivers can be short if their payloads can tolerate very high accelerations, but they need to be long if there's a requirement to accelerate the payloads gently, as would be the case for a human-rated mass driver. A mass driver needs to find an acceptable trade-off between subjecting its payload to too much acceleration and being long and potentially more expensive. The fourth characteristic of a mass driver relates to Newton's third law of motion. Every action must have an equal and opposite reaction. A rocket accelerates by expelling burnt propellant. That burnt propellant is the rocket's reaction mass. A mass driver, on the other hand, is generally anchored to a planetary body, so when it accelerates a vehicle, the reaction mass is the mass of the entire planetary body. A mass driver pushed off against the solid mass of the planet, same as we do when walking or running. We can and probably would run mass drivers at high accelerations, especially cargo pods, but a long and slow mass driver gives us the ability to do low accelerations where it might be needed, like for space tourists who had health conditions limiting acceleration, or acceleration-sensitive cargo. Rockets are also bumpy rides, where a mass driver will generally be smoother and steadier than a rocket. If a mass driver operated at 4 Gs, the trip would only take 199 seconds, or just over 3 minutes, with a track length of 482 miles, 775 kilometers. At 9 Gs, that ride to low orbital velocity would last 88 seconds along a 214-mile, 345-kilometer track. This 9G limit is about the maximum tolerable for most people, and even then, only for those in good health and for short periods. However, shorter tracks with higher acceleration could be used for launching cargo or other materials into space. A great deal of cargo could tolerate accelerations of 100 Gs or even 400 Gs, resulting in launch durations around 8 seconds and 2 seconds respectively. These high acceleration launches are more like cannon shots, requiring track lengths of 19 miles, 31 kilometers, and 5 miles, 8 kilometers, respectively. However, you won't find many mass driver designs based on 400 Gs on Earth, as the track length needed is too short to effectively clear the atmosphere. On the Moon, though, where there is no atmosphere to contend with, a 400 G mass driver would only need a track of about 360 meters, 1,181 feet, or a quarter of a mile, to reach lunar orbit at a speed of 1,680 meters per second, which is roughly 1/5 of Earth's orbital speed. Similarly, a track built up the side of Olympus Mons on Mars could be feasible. Mass drivers are especially popular in lunar concepts for sending fuel, bulk metal, or rock mined on the Moon into space. The engineering challenges are more manageable, and they help avoid issues related to launch pads and moon dust. Mass drivers are also ideal for asteroids, where mines could use them to send materials back to Earth. They can also be used off-planet for sending ships up to interplanetary speeds or even decelerating them, though the latter especially is a tricky topic we won't delve into today. Those are the basics of mass drivers. For a deeper dive, check out our episode dedicated to mass driver technology, though we'll also look more at the engineering and economics in a few minutes. Now let's shift our focus to rockets. The basic premise of rocketry is momentum conservation. Momentum is mass times speed, so if you double an object's speed, you double its momentum. Since momentum must be conserved, any increase in momentum is offset by an equal and opposite momentum elsewhere. When you push off Earth to jump, you actually impart the same momentum to the Earth in the opposite direction. However, because Earth is around 100 billion trillion times more massive than you or I, it gains only a tiny fraction of the speed we do. In the vacuum of space, there's nothing to push against, so rockets propel themselves by ejecting something out of the back of the ship. This propellant can be any material, but in chemical rockets, it's usually the exhaust from the burning fuel. The speed at which this exhaust leaves the rocket is called the exhaust velocity. Generally, the hotter the exhaust, the faster it moves. The molecules of gas in the exhaust also tend to move faster at a given temperature if they are lighter. For example, some rockets burn hydrogen with oxygen. Oxygen atoms are 16 times more massive than hydrogen atoms, which are about 1 AMU, and AMU being about the mass of a proton or neutron. At the same temperature, lone hydrogen atoms move 4 times faster than oxygen atoms because the square root of 16 is 4. While atomic hydrogen would make an excellent propellant due to its speed from temperature, the exhaust particles in most rockets are heavier. For example, in hydrogen-oxygen rockets, the exhaust is primarily water, 18 AMU, and hydrocarbon fuels like RP-1, it includes water and carbon dioxide, 44 AMU. These heavier molecules move significantly slower than lone hydrogen atoms at the same temperature. They are the product of combustion fueling the process though, while lone atoms or small molecules would need to be heated by something like a nuclear light bulb or microwave beam instead, which are topics we've discussed elsewhere if you're curious. As mentioned, bigger molecules move more slowly at the same temperature, so our exhaust products here, water and carbon dioxide, have 18 and 44 AMU as their masses. So at a temperature where carbon dioxide is moving 1,000 meters per second, water is moving 1,563 meters per second. A lone hydrogen atom has a mass of just 1, so hydrogen atom would be moving at a whopping 6,633 meters per second. If we were imagining a drive that was just a big microwave, heating propellant as hot as the chamber could get without melting, and getting its power from a microwave beam aimed at it, we would obviously prefer to use hydrogen as our propellant. We can also do this with a laser. In ion drives, which use electromagnetic force to eject ions as propellant, with something akin to a mini-mass driver, the fuel and oxidizer are typically replaced with an energy source, such as solar or nuclear power, while the ions are the propellant. This can be handy since here, and with other non-combustion drives, like most nuclear drives, your exhaust or propellant can be hot and very high-speed hydrogen as opposed to a heavier combustion product, which again is typically water and carbon dioxide, same as with a gas-powered car. A key challenge for rockets is the need to carry both fuel and oxidizer, unlike cars and airplanes, which draw oxygen from the atmosphere. As altitude increases, air thins out, making it impractical to rely on atmospheric oxygen. While some air-breathing designs, like the synergetic air-breathing rocket engine, SABRE, can function as both jet and rocket, most rockets carry their oxidizer. Oxygen is heavy compared to hydrogen, and in Hydrolox rockets, burning hydrogen and oxygen, only about 11% of the mass is fuel, while 89% is oxidizer. Hydrogen's low density and storage challenges often make kerosene, RP1, a preferred alternative. Kerosene, a mix of hydrocarbons with about 15% hydrogen by mass, produces carbon dioxide and water when burnt. Though less efficient than Hydrolox, it's easier to handle and delivers decent performance when paired with an oxidizer, but it does have a considerably lower exhaust velocity than straight water, let alone lone atoms. Another limitation is the heat rockets can withstand. Hydrolox achieves exhaust velocities around 4,400 meters per second in vacuum, compared to RP1's 3,300 meters per second, but both reach extreme exhaust temperatures of up to 67,000 Fahrenheit or 4,000 Kelvin. These speeds still fall short of the 7,800 meters per second, 17,500 miles per hour, required for low Earth orbit. Doubling an object's speed requires 4 times the energy, and carrying extra fuel adds weight that must also be accelerated, reducing efficiency further. The Tsiolkovsky rocket equation reveals that to double your speed, you need E squared times as much fuel, where E, Euler's number, is approximately 2.718. This means you need about 7.39 times more fuel to double your speed. For triple the speed, which requires 9 times the kinetic energy, you'd need E cubed, or roughly 20.09 times more fuel. Quadrupling the speed requires e to the fourth, or 54.6 times the fuel, and 5 times the speed would need e to the fifth, or 148 times the original fuel amount. This is what we refer to as the tyranny of the rocket equation. When accelerating an object with something heavy to push against, like a planet, the energy required to increase speed scales with the square of the speed. For example, raising speed by a factor of 2, 3, 4, 5, or 6 requires kinetic energy that scales as 4, 9, 16, 25, and 36 respectively. However, for rockets, the fuel needed scales with e squared, e to the third, e to the fourth, and so forth, meaning a factor of 2, 3, 4, 5, or 6 in speed increase requires 7, 20, 55, 148, and 403 times the fuel, respectively. To achieve 20 times the exhaust velocity, a rocket would require around 5 million times the initial fuel needed, reaching speeds of just 70 to 90 kilometers per second with conventional rocket fuel, and even at those speeds, a trip to Alpha Centauri would still take 15,000 to 19,000 years, and would require an impractical amount of propellant. Chemical fuels are not suited for interstellar travel, which is why we explore concepts like atomic rockets. For more on that, see our episodes on the Orion Drive or Medusa Drive. Today though, our focus is on getting off Earth and traveling to destinations relatively close to Earth, such as geostationary orbits, the Moon, and Mars. As awesome as mass drivers and rockets are, their main purpose is to take us to even more interesting places out in the galaxy. And if you're looking for an awesome sci-fi story set out beyond the galaxy, check out Faithless, a Sojourn story, a feature-length audio drama. Follow Castrian and Vadic's perilous journey through the Sanctum, set in the intriguing Sojourn universe, and reminiscent of The Expanse. Faithless is a great addition to the ever-growing Sojourn story. And speaking of ever-growing, every month we release a new and exclusive episode of SFIA, and this month's exclusive, Fermi Paradox Air, we dive into the mysteries of planetary atmospheres and their profound influence on life and civilizations. Could the atmospheres of distant exoplanets be our first signs of alien life? You can watch Faithless, a Sojourn story, and Fermi Paradox Air now on Nebula for less than $3 a month using my code IsaacArthur. Nebula is the largest creator-owned streaming platform, where every SFIA episode airs early and ad-free. Nebula also features tons of exclusive content from myself and many other creators. Sign up at go.nebula.tv/IsaacArthur using the code IsaacArthur to get 40% off an annual plan, making it less than $3 a month. Nebula also offers lifetime memberships and gift options, so you can share awesome content like Faithless and SFA's monthly exclusive with friends and family. Just go to go.nebula.tv/IsaacArthur, and now let's get back to our show. Before we explore the pros and cons of rockets versus mass drivers, I should emphasize that mass drivers are a far less mature technology than rockets are. Humanity has been working on perfecting rockets for close to a century. 2026 will be the 100th anniversary of Goddard's experiments. Mass drivers are a relative newcomer to the field. Gerard K. O'Neill and some of his collaborators such as Henry Combe, Bill Wheaton, Bill Snow, and Kevin Fine, to name a few, developed some prototype coil guns in a lab in the late 1970s. The linear motors used for launching aircraft from aircraft carriers, called the Electromagnetic Aircraft Launch Systems or EMALS, were prototyped in 2009 and were installed on the first aircraft carrier in 2015. So rockets have a huge head start, but as our demand for space access grows, so does the appeal of alternatives to rockets. Recent advancements by SpaceX and others have stimulated the space economy and used rockets to do it, but this growing demand could ultimately drive the development of mass drivers and other non-rocket launch systems. Compared to mass drivers, rockets have a lower upfront cost, or capital cost, but higher operational cost, so they are economically attractive when there is limited demand for access to space. Mass drivers are generally thought of as a technology characterized by a high capital cost but much lower operational costs. Once built, they can launch payloads frequently and at a fraction of the per-launch cost of rockets, making them ideal for high-throughput operations, like moving millions of people or millions of tons of cargo to space. It's not just a drop in energy costs. In truth, fuel is not a large fraction of a modern rocket's costs. Rockets have many complex systems that must operate close to their failure point with minimal redundancy to save weight. It is the cost of achieving extreme performance and reliability relative to component weight that makes rockets expensive. Since mass drivers are fixed infrastructure, more like a bridge or a tunnel, they can be engineered more conservatively. Another driver of change is the growing need to find alternatives to technologies that rely heavily on fossil fuels or that have high greenhouse gas emissions. Mass drivers can be powered by clean, renewable energy sources such as solar, nuclear, or hydro. Solar is particularly advantageous in space environments like at the moon's poles, where the sun's energy is abundant and sustainable. With mass driver technology, there is a clear path forward to electrify space launch, as mass drivers efficiently convert electricity into kinetic energy. The same is not true, for example, of long-haul aviation, as batteries do not yet come anywhere close to aviation fuel on the metric of energy density. On Earth, the long-term reduction in emissions could make them an attractive alternative to rockets as we seek greener launch options. Safety is another strong point for mass drivers. Rockets carry enormous amounts of volatile propellant, which can pose significant risks during launch. They are too dangerous and loud to be near human habitation. This leads to regulations designed to guarantee that the public's interest in safety is consistently prioritized, but which launch providers may find burdensome. People must also evacuate from the area around and downrange of the launch pad. Spacecraft launched with a mass driver are less likely to stray off course as the vehicle travels along a track, and they don't carry much fuel on board, which significantly reduces the risk of explosive accidents in populated areas. When people speculate about why we don't already use mass drivers to launch spacecraft, they sometimes raise concerns such as the difficulty of building a long evacuated tube, or the difficulty of the flight path between the end of the launch tube and the edge of space. But these are problems where reasonable solutions have been proposed, solutions that, on paper at least, do not appear to violate any laws of physics or engineering. Even catastrophic failure of a mass driver causing pieces to fall down from the sky can be handled by including parachutes or building them far from populated areas, and building them in the ocean is also an option as it avoids other issues like acquiring land. The real unsolved problem has been that the kinds of linear motors we have the most experience with become very expensive when we try to scale them up to the kinds of speeds we need for spaceflight. The problem is related to the cost of rapidly converting energy from one form to another. Typically in a mass driver, stored electrical energy is rapidly converted to kinetic energy. Let's assume that we want to accelerate a payload at a steady acceleration from 0 to 8,000 meters per second. It only takes half a joule of energy to accelerate 1 kilogram from 0 to 1 meter per second. It takes roughly 8,000 joules of energy to accelerate that same kilogram from 7,999 meters per second to 8,000 meters per second. So peak power will occur at the end of the mass driver, and that peak power will be proportional to the exit velocity squared. If the mass driver needs to be many kilometers in length to make the levels of acceleration manageable, the power conversion hardware will need to be distributed along the length of the mass driver. Let's imagine that the mass driver is made up of a lot of electromagnets, and each includes some post-power electronics to turn it on and off. Let's assume that this mass driver is designed to accelerate a spacecraft from 0 to 8,000 meters a second at a constant acceleration of 10 Gs, or rounded up to 100 meters per second squared. If you divide the target speed by the acceleration, you get the time it takes to accelerate to 8,000 meters per second, 80 seconds. But in the first second, the spacecraft will travel just 50 meters. In the last second, it will travel 7,950 meters. So the spacecraft travels past many more electromagnets in the last second than it does in the first second. Not only many more electromagnets, but many more copies of the post-power electronics that turn those magnets on and off. When you do the math to add up or integrate the cost of all the higher power energy storage and power conditioning hardware components distributed along the length of the mass driver, the total cost of the hardware works out to be roughly proportional to the cube of the mass driver's muzzle velocity. Still better than a rocket, but crushingly expensive. However, there are newer mass driver architectures that are less reliant on expensive power conditioning hardware distributed along the entire length of the mass driver. One such architecture is the variable pitch screw launcher, a technology we've featured on this channel before. It spins up its screws with electric motors over a long period of time. This reduces the power requirements associated with electrical to kinetic energy conversion, but then the kinetic energy of the screws is transferred directly to the vehicle quickly in a manner that does not require energy conversion and expensive power electronics. To understand how this is done, it might first help to understand how a magnetic gear works. A magnetic gear does the same thing as a normal gear, but instead of relying on mechanical contact between the gear's cogs, it uses magnetic fields that are designed to intermesh with each other. A magnetic gear is like a mechanical gear, except that it works without making physical contact between the gears. A worm gear is another kind of gear, where one of the gears is a spiral and the other is a normal gear. A lead screw with a traveling nut works a bit like a worm gear, except that its spiral gear converts rotation into linear motion. These devices, called magnetic lead screw-driven linear actuators, have been built in some research labs. The variable pitch screw launcher is a kind of magnetic lead screw-driven linear actuator, except that because the screw has a variable pitch, the traveling nut accelerates as the screw turns at a steady speed. With this architecture, electrical energy is gradually converted into kinetic energy of the spinning screws, and also flywheels inside those screws, well in advance of the spacecraft's arrival. Since this energy conversion takes place over many minutes instead of microseconds, the power is low, and thus the cost of power conditioning hardware is low. In fact, this conversion is done using electric motors inside the screws, just like the efficient motors that you would find inside your average mass-produced electric vehicle. Once the screws are sped up to full speed, they continue to spin at a constant RPM. There's a device called an adaptive traveling nut, or just adaptive nut, that magnetically couples to the screw's flights without making direct physical contact. This component is accelerated by the screws, and it pushes a spacecraft on a maglev sled ahead of it down the length of the mass driver. The screws of the variable pitch screw launcher are made out of steel, which is a relatively cheap material. We could imagine even stronger ones able to permit higher launch speeds made of something like graphene, but we don't need it for getting to low orbit. Because the screw stays on Earth, or whatever planet or moon the mass driver is installed on, they don't need to be engineered with the kinds of razor-thin engineering margins that we typically see used in rocket designs, so they are relatively cheap to manufacture. This helps give the technology a capital cost that's affordable within the budget of a major space program. A version of this launcher was presented at the Electromagnetic Launch Conference in Amsterdam in 2024, and also at the Reinventing Space Conference hosted by the British Interplanetary Society. An accompanying paper in the Electromagnetic Launch Conference proceedings discussed an implementation for a 22-year-long Mars Human Outpost space program. It proposed the launcher and its launch vehicles would be used to land a total of 6,152 metric tons of equipment and supplies on Mars, spread out over 10 Mars transfer windows, which is roughly a 20-year period. I'll put links to both of those presentations and the paper in the description if you're interested in learning more, and we might revisit it with its own episode. But I think that the defining characteristic of this kind of mass driver is that its cost scales with the square of its exit velocity, which gives it a big advantage over earlier mass driver architectures, where the cost was dominated by the cost of power electronics, which scaled with the cube of the exit velocity. To appreciate the significance of cost scaling with the square of exit velocity, it helps to plot cost versus velocity on a log-log graph, which for audio-only listeners is up on the screen. Because the cost of the variable pitch screw mass driver scales with the square of its exit velocity, its cost versus velocity curve is a straight line. If velocity doubles, the cost quadruples. The exact position of the line depends on what assumptions you make about, for example, how much payload the launcher launches over its operational lifetime. This curve assumes the launcher launches just 6,152 tons over its lifetime, which would be unlikely given that it could launch tons of other stuff to orbit when not launching to Mars. The cost of rockets is represented by an exponential curve on this graph. The two curves cross at a delta V of around 9,500 meters per second, which is roughly the amount of delta V that a rocket needs to get to low Earth orbit. So these curves show that for trips to low Earth orbit, the cost with a rocket is comparable to the cost of the mass driver. Though again, if we're doing more cargo to low orbit that's not related to Mars, this will go down. We're just demonstrating how cost improves over rockets at even higher speeds. But if our goal is to send a lot of payload mass on its trajectory to the Moon or Mars, then more delta V will be needed. In this case, the cost of rockets rises sharply because it follows the exponential curve. If the mission requires a delta V of 12,300 meters per second, then the mass driver is 10 times cheaper than the rockets. If the mission requires a delta V of 15,000 meters per second, then the mass driver is 100 times cheaper than rockets. If the mission requires a delta V of 17,800 meters per second, then the mass driver is 1,000 times cheaper than the rockets. If the mission requires a delta V of 20,000 meters per second, then the mass driver is 10,000 times cheaper than rockets. If you are planning a mission to Mars and you really want that mission to have a high delta V budget, perhaps because you want to minimize the crew's exposure to space radiation, or if you want that mission to have a high mass budget because you want to send more crew, more spare parts, and beefier habitats like an Aldrin cycler to reduce risk, then these choices drive up the mission cost a lot for an all-chemical rocket architecture. However, if the architecture uses a mass driver, then these kinds of choices will only increase the cost by a small amount. Let's return to some of the other challenges associated with mass drivers and discuss some of the techniques that were proposed to deal with them. One of the challenges is atmospheric heating. In one of the earliest episodes on the channel, I talked about using active structures, such as the Lofstrom loop, to support the entire launcher at an altitude of 80 kilometers to completely avoid most of the aerodynamic drag issues. And that's another launcher system that probably deserves a new and updated episode of its own. A technology called Stellardrone, which we've also discussed about on this channel before, proposed to avoid this problem in the lower atmosphere by enclosing the mass driver within an evacuated tube, and the upper atmosphere by protecting the spacecraft with a thermal protection system. With this concept, the entire mass driver and most of the evacuated tube is on the ground. Some of it is on the side of a mountain, and the rest is held aloft in the air. The Stellardrone concept proposed that the elevated part of the evacuated tube would be supported by using the repulsion of powerful superconducting coils. The variable pitch screw launcher basically uses similar techniques to those proposed by the proponents of Stellardrone. The mass driver portion is on the ground or floating under the surface of a lake or the ocean, underwater so that ships and marine life can still pass by uninhibited. There's a portion where the spacecraft is redirected skywards while traveling inside an upwards curving tunnel cut through a mountain, and there's an elevated evacuated tube portion that the spacecraft coasts through to avoid atmospheric drag within the densest part of the atmosphere. I think the elevated evacuated tube is the hardest part of the architecture to buy into, so let's take a closer look at this idea. Airplanes are essentially big aluminum tubes that fly, quite reliably, at lots of different altitudes. They usually have a positive pressure, meaning that the inside pressure is higher than the outside pressure to help keep passengers comfortable. However, the fuselage of an airliner is designed to handle a certain amount of negative pressure, or overpressure. Some are designed to handle an overpressure of 1 psi with a 1.33 engineering factor. This works out to be about 1/10 of an atmosphere at sea level. That means that the inside pressure is 1 psi lower than the outside pressure. The airplane is designed to be able to fly without imploding. Now, the outside pressure will be perhaps 7 psi at the elevated evacuated tube's lowest point, near the top of a mountain. So it seems feasible that we should be able to engineer a ribbed aluminum tube strong enough to hold a vacuum without making that tube more than 7 times heavier per meter of length than the empty fuselage of a commercial airliner. From an engineering perspective, an elevated evacuated tube would thus be similar to an airliner's fuselage but with a slightly thicker skin, reinforced with more ribs to help maintain its circular shape while under negative pressure, and of course it would be much longer. At lower altitudes it's under higher pressure but is resting on the ground or floating, so we need not worry as much about weight for reinforcing things, much as a submarine can be built to withstand overpressure that would crush us. The next question we need to address is how do we hold that elevated evacuated tube aloft? In an earlier episode we made on tethered ring space launchers, we talked about the possibility of suspending the elevated evacuated tube of the mass drivers from a tethered ring. However, another solution to this problem has been proposed that we haven't talked about before. The solution is to support this tube aeronautically, with drones. We know from drone light shows that large squadrons of drones can be programmed to fly in formation with remarkable precision. Drones that have been designed for crop dusting or package delivery give us a pretty good idea of what it costs per kilogram to be able to lift something with a drone. So the idea is that when each Mars launch window opens, and weather permitting of course, you command thousands of drones that take off and have them carry the evacuated tube up into the atmosphere. These drones can be powered by electricity brought up from the ground using wires on the tube, so they won't need many batteries. The tricky part is perhaps the station keeping. The drones need to be able to keep the tube centered around the spacecraft's projected flight path despite gusts of wind that will want to move the tube out of position. If you're the kind of person who is skeptical about SpaceX's proposal to do a tower catch, you will probably be skeptical about this part of the proposal too. But it is not the kind of thing you have to get right on the first try, like the recent Super Heavy tower catch or the first space shuttle launch. Plus, a drone-heavy economy is likely to do most of the work for this as research for other uses in the economy. You can spend years tweaking the drone hardware and their control algorithms, and you'll be able to test the system in all kinds of weather conditions before attempting to launch a spacecraft through the evacuated tube. So yes, there is certainly an unanswered question here about whether we can make drones that can react quickly enough to keep the evacuated tube centered around the spacecraft's trajectory while dealing with gusts of wind and whatever else nature decides to throw at it. But perhaps it's not a whole lot crazier than the idea of catching a rocket stage out of the air with a pair of giant chopsticks. If that doesn't work, we can always use mega towers or even space towers. See that episode for details. So we can probably make all this work, but obviously, until we get a prototype, we don't know for sure or how well it functions. At the same time, rockets remain the most flexible and accessible option for space launches. Although mass drivers may offer long-term cost savings, the initial investment for rockets is far lower. Building a single rocket costs substantially less than constructing a mass driver, which can make rockets more practical for missions with smaller budgets or lower launch frequencies. This lets smaller companies or countries get into the launch market, which is already a very heavy lift, pardon the pun. This lower upfront cost also allows for greater experimentation and customization, as rockets can be tailored to specific payloads and mission requirements. When it comes to scalability at the low end, where payload volumes are smaller, rockets excel. They can be manufactured in various sizes and configurations to handle everything from small satellite launches to the most costly flagship interplanetary missions. This adaptability makes them suitable for a wide range of payloads, from delicate instruments to crewed spacecraft. Additionally, advances in reusable rocket technology, like those developed by SpaceX, are driving down the per-launch cost and increasing launch frequency, allowing rockets to remain competitive even as other technologies emerge. Safety, while often concerned due to the risks of fuel explosions, is improving with modern rocket designs. Rigorous testing, redundancy, and automation have significantly enhanced launch safety over the past few decades. Moreover, rockets are well understood and widely regulated, with decades of operational experience guiding their safety protocols. The environmental impact of rockets is more complex. At the moment, rocket launches are so infrequent that we can ignore their environmental impact except to local habitats where the facility and launches can be disruptive. We also do have the ability to make carbon-neutral hydrogen fuel for rockets by electrolyzing water powered by renewable energy or nuclear. Overall, rockets provide a proven, adaptable, and cost-effective means of reaching space, particularly as new innovations continue to enhance their safety, environmental impact, and reusability. And as mentioned, for the near term, we would envision using a small, cargo-only mass driver to work in tandem with rocket launches carrying people, sensitive cargoes, or atypical and large ones. To summarize and bring us in for a landing, mass drivers are very promising and offer us a way to get bulk amounts of freight and high passenger numbers to space for a fraction of modern launch costs, but still needs much R&D, while rockets continue to improve and for now are able to satisfy our spaceflight needs. As time passes though, I think a transition to using mass drivers will occur, and that we will see their use on the moon too. Unless of course we end up with something even better, and we do have some other systems we can discuss that we will be pulling over on our YouTube community page, so drop by to vote for which you'd like to see an episode on. In the meantime, whether it's by rockets or mass drivers, we are going to keep getting better at getting into space, because the sky is not the limit on humanity's ambitions or destiny.